So this is going to be an example, another example. I did one in the weighted residual presentations of each method. So what I'm going to do here is just a different example with a different assumed solution, so you can see how it works in just another case. So we have this case of flow that's happening, and we have, this is going to be fully developed laminar flow, so we have this parabolic profile, and we have the governing differential equation. And basically it's reduced down from the Navier-Stokes equation. So if you go back and look into a fluids textbook, you can probably find that for Poiseuille flow. And so what we need to do is we need to take our viscosity to the other side and then do our integration and apply boundary conditions to solve that. So let's do the integration first, and then we'll apply the boundary conditions here to come up with the exact solution. So if we take our, so we got the second derivative of u with respect to y, and we're going to take our mu, our viscosity, to the other side with our constant of our pressure gradient, so dp dx is going to stay constant the whole time. So now we're going to do our integrate once, so we get the first derivative of u with respect to y, and we're going to get 1 over mu, all that times, put dp dx, and then we'll put y here, plus our constant of integration. And then we'll have our, whoops, I got a stray mark going on here, sorry. Let me erase that. There we go. And then we have the second derivative, so we end up with u as a function of y is equal to 1 over mu dp dx y squared over 2 plus c1 times y plus our second constant of integration. All right, so we need to apply boundary conditions to that, and so I'm going to list them here, and then we'll actually do the application on the next slide here. But our boundary conditions are at y equal to 0. If we look over here at our diagram, if we look at y equals 0 here, what is the velocity at that point? And if we look at that point, we can see that u is equal to 0. And then another boundary condition, we can go to the other side, we can say y equal to h, and we see that at that location, we also have u equal to 0, so up here at the top here. So in both those cases, y is equal to 0. So we're going to take those, we're going to apply them to our differential equation to come up with our constant of integration. All right, so our first boundary condition is y equal to 0. At y equals 0, u is equal to 0. So for our function, we got y is equal to 0. So we get 1 over mu dp dx, and 0 for substituting for y, plus c1 times 0 plus c2. And so we can say that all is going to equal 0, so we can find from that therefore c2 is equal to 0. And for our second boundary condition, we have at y equal to h, we also have the velocity is equal to 0. So in that case, we're going to have u as a function of, or where y is equal to h. So we get 1 over mu times dp dx, and now we have h squared over 2 plus c1 times h plus c2, oops, no, c2 is equal to 0, and that all equals 0. And so as a result, we'll find that c1 is equal to negative h over 2 times mu dp dx. So now if we substitute C1 and C2 back into our velocity profile equation, we end up with our velocity profile is u as a function of y is equal to 1 minus 2 mu, 1 over 2 mu, dp dx, all times the quantity of h times y minus y squared. So we get that parabolic profile we were expecting to see, because we know that from the laminar, fully developed laminar profile is going to be parabolic. All right, so now we're going to do this for using the weighted residual formula, and then we're going to compare what we get for different between the exact versus the other weighted residual methods. All right, so we're going to start with kind of the development of the residual equation on the next slide, and then we'll get into collocation, subdomain, and the Galerkin method. All right, so to get the residual equation, we need to come up with, take our governing differential equation and set it equal to, well, it would be equal to 0 if we had the exact solution, but we have the assumed solution. So if we set it equal to 0, that would be for our exact solution, but with the residual equation, we're going to swap out 0 for r. All right, and then we also need to plug into this is we need to substitute for the second derivative our assumed solution. So our assumed solution that we're going to use for this particular case is the following. So we're going to use u as a function of y is assumed to be a, so this is our unknown coefficient, times y to the fourth power minus h cubed times y. So you can see it has a similar form to what we're going to expect from the exact solution. Instead of here would be y squared, and this would be just y by itself times h. So I'm going to go to y to the fourth power, so you can basically see what a similar function would look like and how it would turn out and what we get for the a values. And again, do a second pass through all our different methods here for the weighted residual. All right, so we're going to take both these, but we need to come up with the second derivative of u with respect to y. So let's do the second derivative here. So we take the first derivative, of u with respect to y, and we'll get a times 4 y to the third power minus just h to the third power. So that one's going to go when we do the second derivative. So the second derivative of u with respect to y is equal to a times 12 y squared. All right, so we're going to take that and substitute those in together here. So we're going to bring down our residual equation. We'll bring over our differential equation. And so that all comes out to be mu times the quantity of 12a y squared minus dp dx equals our residual. All right, so that's what we're going to be using as we now implement the collocation, subdomain, and Galerkin methods. All right, so the collocation method is the one where we take the residual equation and we're going to force it to be 0 at a particular point, or points if we have more than one unknown coefficient. In this case, we only have a again, so it's only going to be 1 point, and we're going to do it right at the center of our flow, so at h over 2, where y equals h over 2. So now let's do that. So we'll say r equals 0 at y equals h over 2. And when we do that, we get the following function. We get mu times 12a, and now we got h over 2 squared, substituting there for y, minus dp dx is all equal. We're saying it's forced to 0 there. So now we can solve for a, find out what our unknown coefficient is. And we're going to come up with 1 over 3 mu h squared dp dx. And we're going to take a, now substitute that back in to our velocity profile equation. And we end up with 1 over 3 mu h squared dp dx, all multiplied times y to the fourth minus h cubed times y. All right, so that's our velocity profiling. In the last slide, we'll do the comparison of that to the other methods. All right, so in the subdomain method, what we're going to do is we're going to force our residual function to be 0 over some interval, or actually the number of intervals that we have unknown coefficients. So we only have one unknown coefficient. We need to find a. So the one interval we have is going to be from 0, y equal to 0, to y equal to h. So setting our equation up here, it's going to be integral from 0 to h of the residual equation with respect to dy, and we're going to set that all equal to 0. So substituting in our residual equation, we got from 0 to h. The residual function is our mu times 12a times y squared minus dp dx, which is going to be a constant as we do this integration. And we're going to integrate that over with respect to y. Let's carry out the integration. So we're going to get 12 times mu times a, and we'll get y cubed divided by 3 minus, we're going to get y dp dx, because again that's representing that as a constant, and then we're going to apply, look at things from 0 to h there, integrate over that range, and so we end up with 12 times mu times a, h to the third power divided by 3 minus h dp dx equals 0, and that's going to allow us to solve for a, which is equal to 1 over mu times 4 times h squared dp dx. Alright, so that's our solve for unknown coefficients. Now we're going to take that, plug that back into our velocity assumed solution equation for the velocity profile. So we get 1 over 4 mu h squared dp dx times the quantity of y to the fourth power minus h cubed times y, and that's it. All right, so there we go with our, oops, a little bit messy there, hang on. That's our velocity profile equation for subdomain methods. So now we're going to work on the Galerkin method. So now we're looking at the Galerkin method, and again we're going to force the residual, but in this case the residual equation multiplied times a weighting function, some weighting function, that's what this represents, some weighting function. And we're going to do it over a single interval. So if we have multiple unknown coefficients, we'll have multiple weighting functions, multiple equations, which will force to be 0, but it'll all be over the same interval. All right, so let's set this up for our case here. So we're going to go from 0 to h, and we're going to have our weighting function times r, and we'll do it over dy equals 0. So now let's make our substitutions. So we're going to go from 0 to h, and for a weighting function, it needs to be the same form as the assumed solution. So what we're going to do is we're going to take our assumed solution, we're just going to drop our unknown coefficient, drop the a. So we're going to use y to the fourth minus h cubed times y. That's going to be our weighting function. So again, same form as the assumed solution. Now we substitute in our residual equation, which is our 12 mu times a y squared minus dp dx. And all that we're going to integrate with respect to y equal to 0. All right, for force to be 0. All right, so I've done this already. So we come up with negative 9/7 times mu a h squared, or sorry, not h squared, h to the 7th power, plus 3/10 times h to the 5th dp dx, all that equal to 0. So with that we can solve for a and find that it's equal to 21 over 90 times mu h squared dp dx. So now we have our unknown coefficient solved for, and we take that and we're going to substitute that back in to our assumed solution equation. So we got u as a function of y is equal to 21 over 90 mu times h squared dp dx times the quantity of y to the 4th power minus h cubed times y. And there is our solution or velocity profile using the Galerkin method. All right, so let's go to the final slide and we'll look at comparing all these methods against each other. All right, so now we can compare all of our different solution types here. So to do that, we need to plug in some numbers. So for the viscosity, 0.02 newton seconds per meter squared. For the location, or the overall width of the channel, so it's 0.01 millimeters, or 1 times 10 to the negative fifth meters. For the pressure gradient, -1 times 10 to the 8th pascals per meter. And to find the max velocity, we're going to find the velocity that at y equal to h over 2. So that's where we're going to ultimately plug in and solve for on each of these solution types. All right, so here's our exact solution, our analytical solution. And noting here, so I kind of purposely picked this assumed solution so it's got a similar form, but obviously it's the 4th power, not to the 2nd power here. But it maintains that we can hit the boundary conditions at 0 at the bottom wall and 0 at h, the top wall, so 0 velocity at those locations. What's interesting, though, I was looking at this first term here, and this negative sign is a result of if we multiply this times -1 versus this one, so you can see where that dropped out. But this is 1/2 versus 1/3 versus 1/4 versus 21/90ths. And we got this h squared term that shows up but consistently throughout our assumed solution type problem statement. So again, it's kind of just interesting how all these things show up. Again, this h value doesn't play a whole lot of role. It's going to be a relatively small number because you got this 10 to the -5 and you're going to square that. But with a multiplication, it may become a factor there. All right, so let's see what our solutions come out to be. So for u, at h over 2 for each of our functions, these become, for the exact solution, it's equal to 0.0625 meters per second. For the collocation method, it's 0.0729 meters per second there at the center of the channel. For the subdomain method, we get 0.0547 meters per second, and then for the Galerkin method, 0.0510 meters per second. All right, so just looking these over, we obviously see the collocation overshot the 0.06. Subdomain seems the closest on the underside, and Galerkin a little bit further away. What we want to look is probably the overall profile and see how they fit compared to the exact solution. But again, this would be in a more complex case where you have an idea of what the shape would be, and you put the most appropriate function for that. Seeing a parabola, we probably would have gone something more like this. If I would have done this as my assumed solution, you'd see the exact solution show up here for collocation subdomain. Galerkin may or may not have come up with the exact solution, but it would have been really close. So the reason I did it this way is so you can see the differences between the different values due to the different profile there. All right, so let me know if you have any questions. The main thing I wanted to hit there was the process of going through these solution methods, and I hope that was helpful.